Thank you. Okay, this says NAS. Let's do an NAS mechanism here. Replacing the chlorine with the methoxy nucleophile. Methoxide. Sodium methoxide. Okay, we have this, right? That's ionic, that's plus, that's minus, that's just a spectator ion. We have a nucleophile. Obviously, the oxygen is now bonding to the carbon, the chlorine has left. And it has taken on an additional lone pair. 3 lone pairs there, and now it has 4, right? Everybody good? Okay, first step. Well, what if we indeed attack here? Are we just going to kick that carbon right off and be done? That would give product. But that would be an SN2 mechanism. Attack, kick off leaving group all at the same time. And you don't do SN2 on a trigonoplanar carbon. You only do SN2 on tetrahedral. Okay? You only do SN1 on tetrahedral. We explained all that up there. It's not any of those mechanisms. And also, if we were to add electrons in here, the weakest bond is going to break. And we said this before twice in this course. What's the weaker bond? Single bond to chlorine or pi bond to carbon?
Pi bond to carbon.
Pi bond to carbon. Now my pi bonds aren't drawn in that precisely. Okay? You want to draw it in a little bit more precisely. You know, it's kind of like there. And now either one of these can be pi bond. I'll add electrons here, and I'm going to move this here. Move the electrons away from this carbon, the pi bond out here, and that's going to give what? Well, chlorine is still there. We now bonded to the methoxy, 2 lone pairs there, pi bond here and here. What's on this carbon down here now?
Lone pair.
Lone pair, yes. Okay. I'll try to draw this very precise. Lone pair. And that's a minus charge. Because there's also an H there. Right? Minus charge. This carbon up here has 4 bonds. Neutral. It's also now tetrahedral. Okay? Now, of course, if a minus reacts to the neutral, you're going to make a minus, right? Okay? Charges don't just disappear. So there we go. What do you want to call this? Nucleophilic addition. That's what we did. Nucleophile added to the carbon. Generate this. Now in an EAS, what charge is generated within the ring? Positive. But with an EAS, the ring reacts with a positive or a partial positive or something. Electrophile. Here the ring is reacting with a nucleophile. Electrons are coming in. Okay? Now, is this resin stabilized? It's not aromatic. Okay? And actually, terminology, we would call this non-aromatic, right? Why is it non-aromatic? Because it doesn't have a p orbital here. Okay? It's not fully cyclic conjugated. But is still resonance stabilized. Yeah? Can we draw resonance here? Need to be able to draw resonance of carbocation, cations in the ring, but also anions. These electrons can come here, and these can move out. That would give here. The old in and out method resonance, yeah? And then these electrons we can move them here and move these out here. Yeah? Okay. What's the truth? Any other resonance structures possible? What?
Any electrons on the oxygen
Do what?
and come in, like, come back that way, then not those pi electrons back to the left.
What pi electrons? Do it on your paper or do it on your, what are you trying to show? These electrons come in and kick off a sigma bond?
No, the electrons off to the chlorine.
Well, that wouldn't be a resonance structure. You want to break the chlorine bond? You'd be breaking a sigma bond. Doing resonance, we don't do anything with sigma bonds, only pi bonds. My question was, is there any other resonance structures? What? Yes, there are no other resonance structures. The only thing you can do here, there's no p orbital here. It's game over. Dead end there. You come this way, electrons can move here, and let them just take you back here. Okay? All right, we have 3 resonance structures. What's the hybrid look like? Partial what?
Partial negative.
I thought you said partial positive for a minute. You didn't say that there. Where do we have, what do we have? Double bond character here, 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 here. Yeah? Partial minus, partial minus, partial minus. Does that look like the hybrid? See, electrons are kind of smeared all through there. That's the average or whatever. If we could take a picture of this. How many intermediates on the board so far? How many intermediates on the board? One, there it is. You see it? That's 1. You didn't think it was 3, did you? No. It's that. When the nucleophile comes in, we form this. So that's kind of cumbersome to draw. We draw fake structures and we say it. Okay, right? Okay. There's your single intermediate. Okay. Are we going to have another intermediate? Actually, no. The next step is, now you can always work with any resonance structure. I could work over here. Now you don't have different colored pens. That's why I don't like using different colored ink. Right? And I don't even have different colored ink. I do have a black here. The next step is these electrons come back, but instead of kicking off the methoxy, they come back in and we kick off the chlorine. Now you can work with any resonance structure. If you want to do it over here, you can do this. It's cleaner over here. I don't have all these errors. These electrons do what? They move in here to make pi bond and kick off the chlorine. You can work with any fake resonance structure. Much harder to work with the real thing. What would you do with the real thing? Okay, right? It's cumbersome, right? So we work with fake structures. That's what we do with organic chemistry. They're easy to, okay? And when this comes in and kicks that off, what do you get? The product. Now the pi bonds may be moved in the ring. You can always move those. That's just another resonance structure of the pi bonds in the ring. Okay? Now what do you want to call this last step? The first one was nucleophilic addition. What do you want to call this? Elimination of the leaving group. That's why I call it, this is an NAS mechanism. It's also called simply an addition elimination. right? And overall equals a substitution. The methoxy replaced the chlorine. We substitute the chlorine with the methoxy. Was it an SN1 substitution? No. Was it an SN2 substitution? No. What's the name of this substitution? It's an additional elimination, but that's a general term. This is a nucleophilic aromatic substitution. That's what this is called. The ring reacted with a nucleophile. All right? Questions about this mechanism? We also did additional elimination back when we did like tosyl chloride, week 1. And we added to the sulfur and the pi bond went, because we said anytime when we come in here, we're going to break the weaker bond. Is it the sigma bond to chlorine or the pi bond to carbon? Pi bond to carbon is weaker. And once we did that, we're no longer doing SN1 or SN2 because the first step is not either SN1 or SN2. Okay, well I got bad news for you. The reaction and mechanism I just showed you does not work. Okay? Specifically, the reaction does not work. This does not happen. Why? Let's do a reaction coordinate diagram. And if we have here A, B, this thing is one thing, right? There it is over there on the left. And C, I'm not going to label the axes here for you. You can do that. We'll save some ink here. What do we got? A. Where's B? B higher. Uh-huh. Yeah. Okay. B. And where's C? I'm not going to try to distinguish between A and C. They're pretty darn similar. Okay? Same number of pi bonds. I'm going to stay back here. Okay. Here we go. All right. Oh! I need some activation. I need a transition state complex, activated complex, activation energy. And then from here, it doesn't take much activation energy to fall downhill, does it? Which one's the rate determining step? First step, making the high energy carbanion. Even though it's resonance stabilized, it's still a carbanion. It's still charged, and it is thus higher energy. Okay? But I'm telling you this reaction doesn't work. Explain why it doesn't work, apparently. Do what? The energy required too high. That's usually why things don't work. Okay? Molecules aren't like just stubborn, or they just don't want to obey their parents. No, it comes down to energy. Okay? Yes. Apparently it's too high. Even though it's resonance stabilized. It's just a carbanion. Too high.
If you heated it, would it do it?
No, it wouldn't. It would do a different mechanism. But we could give it more energy. You could say, well, let's just apply heat. I said mild heat. Higher heat will actually give a different mechanism. Okay. The only way to make this reaction work is to change the reactant. We've got to stabilize this more. We've got to bring this down. How can we bring down the energy of the intermediate? I had 3 resonance structures. How could I make it even more stable? More resonance. But we said there is no more. We're going to have to modify this. This won't react, but if we take here and put a group here, like a ketone, and I put it ortho to the chlorine, I put a methyl ketone here. Now the reaction will work. What does that do? Hope you got room to draw this in. If that was here, Okay, every place, let's draw in a methyl ketone. Can we now draw an additional resonance structure for our carbanion? Yes. Because these electrons here, I'll go back to blue, instead of coming this way for resonance, what if we brought them here and moved these here? In, out, in, out, in, out. What would that give? Okay. I'll come this way. And we'll have what? Somebody have that resonance structure? You've got to be able to draw resonance structures for cations and anions. We did it back in September. Somebody got the resonance? Somebody got it? I just want to see it. Uh-huh. You confident in how to draw resonance? You got that? You didn't just guess. You did it right. Right, it's arrow movement, right? Okay. You got it? Okay. Well, what does this arrow mean? I bond here, make second bond here, and then these electrons are moving, well that methyl's there, out onto oxygen to become what? Third lone pair? And indeed, it is now minus, because remember the golden rules of resonance? Remember that was a free handout, I didn't charge you for that. Golden rules of resonance? Okay. One of the golden rules was all resonance structures have the same net charge. So if all those are minus, this has got to be minus. Regardless, it's kind of here. Okay? There you go. We have an additional resonance that stabilizes the intermediate. But more importantly, it's not just any old resonance structure. Here, the charge is on carbon, minus on carbon, minus on carbon. Where's the minus now? On oxygen. And that's an even better thing. Okay? The minus charge we're able to place on an electronegative atom. Good thing. And now, with the ketone there, let's call that B prime. Now B prime is more like here. Everybody agree that as a result of my modification of adding this ketone group, the intermediate is now more stabilized? Okay, we can lower it down. And now we can do this. And we can do a reaction here. And now it will work. I'm just telling you that this will work. And I'm just telling you, you can't just raise the heat and get that to work. There's a divide here. And the NAS, okay. All right. Let me ask you this. Could we put the ketone anywhere, or do you have to put it in certain positions? It has to be ortho pair. How do you know that? Where did the charge fall in the ring compared to the reaction site? Ortho? Para? Ortho. Only if that group here, which you do resonance, falls on those same carbons can you do resonance there. Because if the group was here, you can look at it. If the ketone was here, we would not be able to draw the additional resonance structure. Try that on your own. You won't be able to do it. The group that you do resonance into has to be ortho or para. To what? To the leaving group. Before you look down here, question. Does the leaving group leave in the rate determining step? No, it does not. Does everybody agree that leaving group leaves in the fast step? I moved the handout. Okay, think back to SN1, SN2. In both of those mechanisms, the leaving group leaves in the rate determining step. Yes, they do. And that's why you have strict leaving group requirements for SN1, SN2. Here, the leaving group leaves in the fast step. Because of that, much less strict than SN1, SN2. Leaving groups. What's good leaving groups for SN1, SN2? Iodide, bromine. Chlorine is okay, it's just not as good. And what else? Tosylate. Positive oxygen, protonate and OH. You can even protonate and nitrogen. Okay? In the NAS mechanism, you'll see many more different leaving groups. Okay? If you've ever seen it be a minus, it can be a leaving group in NAS. Because it leaves in the fast step, and fast steps are easy. Okay? You'll see some weird leaving groups in NAS. It won't be a plain carbon or H. It has to be able to somehow support a minus charge, because it does end up as a minus, like Cl minus. Okay? Also, look at this. In terms of your halogens, an F is a better leaving group than iodine. That's totally different from SN1, SN2, right? Why is F a better leaving group for NAS?
Because it's more electronegative, so it's easier to leave.
No, it's not easier for it to leave.
It's easier for it to...
First off, two things. No, iodine is easier to leave. That's why iodine is a better leaving group in the SN1, SN2. Why does iodine leave easier? Because the CI bond is weaker, and you're breaking the bond in the rate determining step. Are you breaking the leaving group bond in the rate determining step here? No. So why talk about leaving? You need to talk about something else. Right here. What's the rate determining step of this mechanism? Nucleophile coming in. Which one of these is the nucleophile going to be more attracted to and thus come in easier? This one. Why? There's more partial plus here. Because the F is more electronegative. That's supposed to be bigger than this. Or iodine would be even smaller, right? So F is a better leaving group, not because it leaves. When we say it's a better leaving group, that's just, okay, which is easier to replace? The F. Not because it's a better leaving group. See, it's kind of semantics here. It's like, well, then why are you calling it a better leaving group? The reason it's a better leaving group is nothing about it leaving, it's because it being there makes more of a partial positive here. And so the nucleophile is floating around, it's like, ooh, I'm going to react over here. And so it reacts faster and easier. And then you say, F reacted faster. It must be the better leaving group. Okay? What's the requirement? I think we stated it. The requirement is right here. We need to put the anion in this form in an electronegative atom. How do you do that? Additional resonance. How do you do that? You need a group that you can do resonance in on the ring. But where does it need to be? It needs to be ortho or pair. Question?
So basically, the only way that we would know that the first reaction didn't happen was because the negative would not be on the electronegative atom.
Right. If you don't got the ketone there, you'll have my original three structures, and it turns out that that just doesn't happen. It looks reasonable. You say, hey, it's resonance stabilized. Yeah, it's all good. If you go to lab, the reaction I originally shown just doesn't work. But we know that if you have this on there instead, it will work. So the NAS has a requirement. I circled it. Let's do an example. Some examples. That's a classical, well, it's more than an example, it's an illustration. It's an example, but you probably already given it. Again, F is a common leaving group for NAS. In my example here, I used a ketone as the electron withdrawing group. Okay, I didn't call that there, but typically this group we're talking about is going to be an electron withdrawing group. And usually these are going to be group 4. My example, ketone. Isn't ketone a group 4 substituent? Yeah. What are other group 4 substituents? Nitro. Okay. You need to know the structure of nitro and be able to draw resonance structures into the nitro group. I'm not going to draw the full structure, but if we had a nitro, and if there was an anion here, I'm not going to complete this up here. Okay. Can't you draw resonance into this? Yeah. These electrons here, and these electrons there. The same as we did right here. The only difference is that's a nitrogen instead of carbon, and that's an O- instead of a CH3. All right, I'm not going to draw that. But the nitro group is a common group for terminology back over here. Can we say that the ketone group activated this for NAS? Because without it, it didn't happen. So the ketone group activated it for reacting. But I thought a ketone group was a deactivator. A ketone is a deactivator for EAS, but it's an activator for NAS. Now, most books are not going to say this, activator. They'll just let you be confused and never clarify it. And then when someone says, hey, yes, the ketone activated the reaction, which it did, right? Didn't everybody agree it did? Because before there it didn't react. Then you'd be like, but I thought a ketone was a deactivator. Well, where they go wrong is they don't explain that, yes, it is a deactivator for EAS, but it's an activator for NAS. Because NAS, we have anions in the ring. And how do you stabilize anions? You want withdrawal groups. Strong withdrawal groups are better for stabilizing these. Okay? So yes, just the opposite for NAS. And so very often people will say activator, and you'll be like, what? Okay. Know that the difference between EAS and NAS. And a nitro group is a great activator for NAS chemistry. Okay, here you go. And where is it compared to the leaving group? Para. There you go. You see how the SH nucleophile, okay, you should know the mechanism for that. That's an NAS mechanism. We need to erase this. One below. Take that tetrasubstituted aromatic reacting with ammonia. Obviously it displaces the chlorine. Why? We got to be careful. It could displace the bromine. More importantly, its position. Maybe I didn't quite hear you. Which halogen is activated for NAS by a strong electron withdrawing group? Does the bromine have a strong electron withdrawing group, ortho or para?
No.
No, they're both meta. Does the chlorine have a strong electron withdrawing group, ortho or pair? Not only one, but two. One is a good activator, two would be even more activated. Because imagine if there were two ketones on this thing. You could get one resonance structure here, but if there was here, you could do another resonance structure here. What if there was three ketones? You'd be able to draw, if they were all here, here, and here, you'd be able to draw three additional resonance structures with each one having charge on oxygen. So there, the ammonia displaces the chlorine. Something's got to take an H from the nitrogen to go neutral. Cl minus can take an H. That's how we got HCl. Well, possibly you might include a base in this reaction to take the HCl. Okay? Or two equivalents. We'll point this out. You may use excess NH3. If you did, you would make over here, you'd make ammonium chloride. And that's where the second ammonia takes the H from the first. And so the second ammonia has reacted with the HCl. Okay, the next one I think is up to you. Can you show product to the next one? See that? That intermediate is just too high in energy up there. Let's look complex molecule a little bit larger than normal. Reason is because this is a drug synthesis that I'm showing you. What do you suspect here? What's going on? Chemistry. We've got an aromatic ring here. Is that electrophile or nucleophile? It's actually got two nitrogens. Only one's going to react in this example, theoretically two. Okay. What type of chemistry is going on here? EAS or NAS? So I assume you're looking for a traditional leaving group. Does a leaving group have a strong electron withdrawing group, ortho or para? Which one? Top or bottom? Bottom. Ortho, nothing. But para, here, a ketone. What about this one? Does it have a strong electron withdrawing group, ortho or para? Ortho, no. Para?
Yes.
That's not a strong electron withdrawing group. That's group 1, the nitrogen lone pair. If the anion is here, you're not going to be able to do any resonance here. But if an anion is here, can you do resonance? Yeah. Okay. The lower one. And the product here is going to be I won't redraw the whole thing. I'll just hit it. I'll just cut it off over there. The rest is over there. Now, instead of the F, we have this, and we have that is a 6-membered ring. Does that look right? Plus what? If we balance it out, we just use one equivalent plus HF. The probability you'd want to use excess of this or some other type of base to react with that HF. So you don't usually want to form a strong acid in a reaction for various reasons. Okay. And the compound we just made is Cipro, a common antibiotic. This is Cipro. The organic one, I use that several times in problems. Product of this next reaction. Methoxide nucleophile.
No reaction.
Anybody else? No reaction. Traditional leaving group, perhaps? Does it have a strong electron withdrawing group, orthopair? No, only meta. No reaction. We can clarify this. No NAS reaction. Maybe there's some other mechanism that could take place. And the next mechanism will be over here. Please be reading about it. It's quite interesting. It's called a benzyme mechanism. It's an elimination addition mechanism. Video key posted later this afternoon. Have a good day, guys.